All right, so this is where we left off. So we're going to kind of move to the next concept of redox titrations. Now, just remember, titrations is just a laboratory technique of a way to mix two chemicals. And generally, the point of a titration is just to find an unknown concentration of one of the species. Now, in order to do that, you have to know the concentration of one of them in order to find the unknown. So again, this is just like a laboratory technique of a way of finding an unknown concentration. And specifically, we're going to do a redox reaction now instead of an acid-base reaction. So let's look at the wording on all of this. So this says manganate 7, which is permanganate. Okay, permanganate. Last class decided that that is like a really funny, weird sounding word. It is. Ooh, I don't like that. Too big. Okay, so permanganate is MnO4 minus. So they call this manganate 7. And you go, oh, well, why do they do that? Okay, well, oxygen is -2. -2 times 4 is -8, which makes manganese +7, right? Because the overall charge is -1. So that is why they call it manganate 7, because the manganese is 7 plus 7. Now, if you didn't know this, you need to know this now. Permanganate is purple in solution. It is a purple species in solution. So it says when permanganate ions act as oxidizing agents. So they're telling you it's an oxidizing agent. What does that tell you about the permanganate? It tells you that the permanganate likes to be what? Anyone? If it's the oxidizing agent, it gets, let's see, reduced. Very, very good. Reduced. So it's the reduced species. And even in the wording it says, so they put it in an acidic solution and they are reducing it to manganese 2 plus. So really they're taking manganese 7 plus and they're turning it into manganese 2 plus. Questions so far? So look at the numbers getting smaller. It's being reduced. It's being reduced by taking in electrons. That's reduction. According to the half reaction below. So this is just a half reaction of the reduction of manganese. And in these titrations, the permanganate solution is placed in the burette and no indicator is needed because this guy is already purple. And at the end, when the manganese gets fully reduced to manganese 2 plus ion, this guy is actually like a light pink color. So it's almost like an automatically built-in indicator because the solutions are colored. So you don't even need an indicator for the endpoint because the solutions themselves are like their own indicators, which is kind of neat for redox reactions. Um, just also to clarify, we talk a lot about these ions, permanganate, right? If I were to go, so like Flynn Scientific is a company I buy a lot of our chemicals from. So if I were to go to Flynn Scientific, I can't just go buy permanganate. It doesn't exist. You have to have some sort of salt of permanganate, like potassium permanganate or sodium permanganate or lithium permanganate that can give us the permanganate ions. But you can't just go buy permanganate. So this is going to come into play a little bit later in the notes. Okay, so here we go. We're going to do our first redox titration problem. So it says a sample of iron ore. Does anybody know what iron ore means?
Iron in solid form?
It's iron in the solid form, but it's like not, it's like impure iron. So like they would have to isolate the iron. It's like iron and a bunch of other junk, like probably in some sort of rock formation, okay? So they take this sample of iron ore and they dissolve it in acid. And the reason that they use acid is because most transition metals, if you like drop them in water, they don't do anything. They'll just like sink to the bottom and do nothing. So in order to get this iron sample to dissolve, you have to use something stronger like an acid. So all of the iron that's in the sample is now turned into iron ion when it dissolves. So let's look at that visually. So you have this sample of iron. Okay, you just got this sample of iron, or it's like iron and a bunch of other stuff, solid form, iron and then like other stuff. Okay, they take it and they mix it with some sort of acid. Okay, so they drop it in here and then they add acid. Sorry, that was very poorly written. Add acid. And then the iron and all the other stuff dissolves also. But really, in this question, we're just going to focus on the iron. The iron from the sample has now become iron ions. Iron 2 plus ions just floating around everywhere in here, and probably a bunch of other stuff. Okay? So let's go back to the problem. Okay, so once they get the iron to dissolve, the sample is then titrated with a molarity and a volume of permanganate solution. A molarity and a volume of permanganate solution. When you see this right here, oh, what? Oops, sorry. When you see molarity and volume in this class, what should you know that you have? Molarity and volume gets you what? Moles. This is a super duper important concept in this class. Molarity and volume gets you moles. So off the bat, we already know how many moles of permanganate solution are being used. So they say the oxidation reduction reaction that occurred during the titration is as follows, and they give you a balanced redox reaction. So before we move on, I don't ask you this question, but it does matter. I just want to talk about it, right? The manganese is +7, the iron is +2, this manganese is +2, and this iron is +3. The hydrogens are +1 and the oxygens are -2, so they don't change. So it's really manganese that's changing and iron that's changing. So just out of curiosity, which substance is being reduced? Which one is gaining electrons or being reduced? Reduced means the number is getting smaller, right? That's what a reduced means. Who is that? Permanganate, or specifically, it's the manganese. So this is my reduction half reaction, which means by default the iron is oxidized, but let's talk about why. Look, it's going from +2 to +3. Losing electrons is oxidation. It's obviously losing electrons. That's how it's turning more positive. Okay? So I'm going to get rid of this now. All right, so the first question says, how many moles of permanganate were added to the solution? Well, this is really easy. Molarity and volume gets you moles, so let's do it. Molarity times volume is moles. So, oh shoot, I already forgot the numbers. 0.02240. I'm going to do this down here. 0.02240 moles per liter of permanganate times, let's see, what did they use? 47.20 milliliters. So in liters, it's 0.04720 liters. So that's going to get me moles of my permanganate. So we grab our calculators. 0.0224 times 0.04720, and you end up with part A, which the answer is 0.01057 moles of permanganate solution. So that's A. B asks for how many moles of iron ion were in the sample. Any suggestions on how I do that? If I have moles of permanganate, what can I do? I have my moles of my permanganate. How do I find moles of iron in the sample? Mole to mole ratios. Beautiful. Good job. So let's do it. 0.01057 moles of permanganate. And then you look at the balanced redox reaction, which they already gave you. It says for 1 mole of every permanganate, it's 5 moles of iron, if I'm not mistaken, ion present, Fe2 plus. So you multiply that number by 5, oops, and you get 0.00526 moles of iron ion. So this is B. Question so far? Okay. Part C says, how many grams of iron were in the sample? Well, on this problem, all of this iron, or I should say this iron, whatever, is assumed to have come from the iron ore. So if you know how much of this guy you have, you know how much of this guy you have. All of the source of iron is the iron ore. So all of the iron present in here comes from here. So if you know moles of iron, you can just turn that into grams of iron. Oops, sorry about that. So I'm going to do a different color so that we don't kind of mix these up. I have 0.005286 moles of ion, which is coming from the iron sample, and 1 mole of iron, or iron ion, it doesn't matter what you call it at this point, is, let's see, where's Fe? 55.85 grams. 55.85 grams. So times 55.85. And we get 0.2952 grams of iron. Okay, so this is part C. So now part D is going to ask us mass percent. So they say, okay, well, if the iron ore, so that's the iron and all the other junk that's in it, had a mass of 0.8890, what is the mass percent of just the iron? So we're going to take the mass of the iron, divide it by total mass of the sample, and then to do percent, as always, we multiply by 100. Let me look at that again, 0.8890. Okay, so mass of the iron. Oops, I'm on the eraser, sorry. Mass of the iron, 0.2952 grams, divided by 0.8890 grams, times 100. And we get 33.21% of it is iron. Now, here's something that is challenging. I just walked you through this problem step by step by step to get to here, part D. Often on the AP test, sometimes, I guess not often, but sometimes they don't do this. They give you this, and they completely omit this part. Meaning you have to understand how to get here without necessarily being spoon-fed the directions. So I'm just pointing it out that it is fair game to be given the statement, the reaction, and just part D, and it is expected you to work through the process on your own without a step-by-step help. Okay? Do you have any questions about this redox titration problem? Okay, one more and then we'll be finished. So, this next one's going to be a lot more complicated. It's not crazy amounts more complicated, but it's definitely more complicated. So I'm going to walk you through the problem step by step. I know I've told you this before, but I know I talk a lot and I don't necessarily write everything down I say. But when I'm trying to give you like hints or ways to recognize what kind of problem it is or where to go with the problem, it's probably going to be a good idea for you to write those hints down so that when you're working on problems on your own, they become helpful to you. So I'm going to go through this problem like pretty much sentence by sentence so we can kind of break it down so that you can break it down. So iodate ions. First thing, iodate ions. So I'm going to look down here at my two reactions. I would like you to circle iodate ions, please. Here they are. Iodate ions. It's these guys. React with iodide ions. Okay, where's my iodide ions? Right here. According to the equation below. So here it is. A sample of sodium iodate, and you go, what? Sodium iodate? I don't see sodium iodate down here. Do you? Does anybody see sodium iodate? Let's see what we got in this chat. Okay, I know you say no, but you should. This is the sodium iodate. This is the source of iodate ions. I was telling you earlier, I can't just go buy iodate. I have to buy a salt that has iodate in it. Sodium iodate, potassium iodate, lithium iodate, whatever. You can't just go to a store and buy or go to a chemical company and buy iodate. So you go, well, what about the sodium? Well, what do you think happened to the sodium? Why isn't it in here? Because it's a spectator ion, so they don't include it. Why? Because it's literally not participating in the reaction. This is likely a net ionic equation, so they've omitted spectator ions. But the sodium iodate is this guy. That's how we get iodate ions in there. Are there questions on that? Okay. So they take a certain mass of sodium iodate, specifically this number, and they dissolve it in water and make 250 milliliters. So, this sentence right here, what are they doing? So, they're taking sodium iodate, they're dumping it in here, and they're making 250 milliliters of solution. In other words, they are preparing a solution. Okay, so now what's floating around in here? So now you have sodium ions and you have iodate ions all floating around in here, all over the place. How many? Depends on the concentration. Which brings me to my next question. Do we have enough information to know the concentration of this solution? I have grams of my solute and I have volume of solution. Do you know the concentration of the solution, or can you find it out? Yes. How do you do that? You turn grams into moles and you take moles and divide by liters. That is molarity. Please do it. And I'm going to do it with you also. So let's see. So they used 0.311 grams of sodium iodate. This is how they got iodate ions. I'm going to look it up. I looked it up last class, so it should pop up hopefully. Sodium iodate molar mass is 197.89. Grams for every 1 mole. So that gives me 0.00157 something something something. I'm going to leave the whole number in my calculators. Moles divided by volume was given. They told you the volume of the solution. It's 250 milliliters, which is 0.250 liters. So the concentration of the solution is 0.00629 molar sodium iodate. Question so far? All right, let's go back. So I've only gotten to this second sentence, all right? So now they're going to take a small portion of it, 25 milliliters, which means they're going to take this container and they're going to measure out a 25 milliliter sample of it, 25 milliliters of this guy. They'll probably measure it in a graduated cylinder and then to dump it into an Erlenmeyer flask to do the titration. So you take this flask, okay, it goes in here. You have 25 milliliters of sodium iodate solution in here. Okay, and they say they start titrating it with potassium iodide. Do you see potassium iodide in any of these reactions? Anywhere? I'm going to use a different color. It's been dissolved, yes, but see, they're reacting the iodate with potassium iodide. This is iodide, right? Where's the K? So it's this guy. Potassium iodide gives me iodide ions. Where's the potassium? The potassium is a spectator. It does not participate in the reaction, so they just don't include it right here. They could just as easily have done this, NaIO3 plus Ki. Okay? but they didn't. They got rid of, in any ways, they'd break apart, right? Because they'd get sodium iodide, potassium iodate, which is soluble, and so the potassium would cancel out. Anyways, I'm going to erase this. So the source of the iodide ions is potassium iodide. The source of the iodate ions is the sodium iodate. They react them together, and then this is what's produced. This iodine right here. This is what's produced. Okay? This iodine is not iodide. This is, I guess, 0, no oxidation state. This is -1. Okay? So the sodium iodate and the potassium iodide make iodine. Why is this here? Oops, I didn't want that color. Why are these H pluses here? Remember that the potassium iodide had been dissolved in sulfuric acid. Hydrogen ions represent the presence of an acid. Okay? So the reason this is here is because of the acid, and yes, it is balanced out with water. So that's a very good point. But the source of the hydrogen ions is the sulfuric acid. Remember, H plus represents acids. Question so far? Okay. So pretty much they take these two, they mix them, they get this, and then they take this substance and react it. So they take this guy right here, here it is, and they react it with sodium thiosulfate. Any suspect of who that is? Sodium thiosulfate. Any suspect of who that is? Good, thank you, Ryan. It's this guy. Why? Well, this guy's name is thiosulfate. It's one of your polyatomic ions. So this is your sodium thiosulfate. Where's the sodium? Who cares? It's a spectator ion. It doesn't participate in the reaction, so they just did not include it in the net ionic equation. So they take the two substances, they mix them and get iodine. And then they react the iodine or titrate it with sodium thiosulfate. Now they tell you the average volume of the sodium thiosulfate is 12.5 milliliters. So that's about how much they needed to add to get to the equivalence point or end point of the titration. So 12.5 milliliters on average is how much they were needing of this guy to get to the equivalence point between this guy and this guy. So then they say, what is the molarity of the thiosulfate, S2O3 2-? Well, what two things do you need to know to find molarity? There's two things you must know to find molarity.
Moles and volume.
Good. Moles of thiosulfate and volume, which is going to be liters. Sorry, my dogs. Volume in liters. So my question to you is, they ask for the molarity. They want this right here. And you need moles and you need liters. Do we already have half of this? There's two variables we need. Or not two variables, two things we need. Do we have one of the two? You have volume. Good, you do. We have volume. It said we needed 12.5 milliliters of this guy. So this is 0.0125 already off the bat. So really what we are trying to find in this problem is moles of thiosulfate. Now, because we're doing a chemical reaction and we're kind of like jumping around from substance to substance, we're obviously going to have to end up doing mole to mole ratios. So, having said that, we said earlier that we knew not earlier, we haven't said this yet. We know the molarity of the iodate. What else do we know about the iodate? So we have molarity. Do you know anything else about the iodate? Well, we don't have moles yet, but we have enough to get to moles, right? We have molarity right here. And then what else do we have? We know how much of the sodium iodate was used. 25 milliliters of it was used. So we have molarity and we have volume. Guess what molarity and volume gets us? Moles. Okay, so let's do that. Molarity of the sodium iodate times the volume of the sodium iodate is 0.025 liters. This will give you moles of sodium iodate or iodate, however you want to call it. So I'm going to write this number right here. This is 1.57 times 10 to the negative fourth moles of iodate reacting. Now what? Is there a middleman in here in my two reactions? Is there a middleman? Meaning is like, does one thing go to one and then it turns into something else? And the answer is yes. The middleman is iodine. The iodine is produced here and then consumed here. So if we go from here to here, we can then go from here to here. Now, why don't we care about the iodide? Does anybody know? Do you have any mathematical information about the iodide or the potassium iodide? Did they tell you how much you had of it? Do you see any numbers that belong to potassium iodide? Hopefully you're telling me no. The 25 milliliter portions are of the sodium iodate. They're being added to iodide, potassium iodide, but they don't tell you how much potassium iodide. You know nothing mathematically about the potassium iodide. So it's kind of assumed that obviously the iodate is the limiting reactant and there's just some set number of iodide. Who knows? Now, here's what's messy. It's not messy in this problem. What if I gave you a molarity and volume of potassium iodide in this problem? If I gave you a molarity and volume, oh Micah, great job, molarity and volume of potassium iodide, you would know the moles of potassium iodide, but you also know the moles of the iodate, meaning it would be a limiting reactant problem to figure out the iodine. But it's not. I did not give you any numbers associated with the iodide, so we're just going to use our iodate to jump to iodine. So let's do that. It's a 1-to-3 ratio. So for every 1 mole of iodate that react, 3 moles of iodine are produced. Okay, so now I'm at moles of iodine. Any suggestions of what I do next? So I'm here, I have moles of iodine. Is the iodine reacting with the thiosulfate? Yes. So I can jump from iodine here of how it reacts with the thiosulfate. So you just do another mole ratio. For every 1 mole of iodine now reacting, 2 moles of thiosulfate react. That's from my second bounce equation. Oh, look! Now I have moles of thiosulfate. I take my moles, I divide by liters, and there is my molarity. So I'm going to work this number out, and I'm going to write it in a different color. So 1.57 times 10 to the negative fourth multiplied by 3 multiplied by 2. The moles, not molarity, the moles of thiosulfate is 9.435 times 10 to the negative fourth moles of thiosulfate divided by how much thiosulfate on average were they using? Well, they were using on average 12.5 milliliters of it. So that's 0.0125 liters. So the molarity of the thiosulfate is 0.0755 molar. Thiosulfate or sodium thiosulfate, whoever it is, S2O32 minus. Whew. How are we doing? Any questions? Okay, so this is where I'm ending notes. However, I do need to talk to you about something. These are FRQs you need to practice on your own. So you can either do them right now. There's like 30 minutes left of class. You could also work on your titration lab, but both need to be completed today. So this is FRQ 2003. This is back in the day they had like multiple versions. So this is version B. So number 5. So number 5. These represent the parts that you need to do. So pretty much the whole thing. You need to do A, B, C, D, E. You have all of the tools to do this FRQ at this point. Okay, same thing with here. You have all of the tools to do this FRQ right here. You have to do all parts, A, B, C, D, E, F. And then this last one is only part A. Number 8, part A. That's it. That's all I need you to do on this one. Now, I'm not going over these with you in class because I really need you to kind of take everything you've learned so far and try to work through these types of problems. They all relate to the content we've been doing. I am, however, going to record me working out the problems, and I will publish it for you to follow. And I'll also publish it so that you can kind of see how the College Board grades and where they assign points and such. But I'm not going to do it right away because I really want you to work on these on your own and kind of test your understanding of these kind of redox reactions. So this is going to be independent learning. So I'm going to kind of set you free. I'm going to hang out here if you want to stay around or if you want to ask questions. But the rest of this is going to be for you to work on these 3 FRQs, and then, or you could be working on the titration lab, the acid-base one. Both are due, both should be finished today. And then the redox I'll move to Sunday.